Welcome to today's session where we will tackle an interesting problem from LeetCode, problem number 1946, largest number after mutating substring. In this problem, you'll learn how to manipulate substrings and apply mutations to maximize numerical values. Let's dive in and break it down step by step. In this problem, we are tasked with mutating a given string of digits, called number, to create the largest possible number. The string number represents a large integer, and we are also provided with an array called change of length 10. This change array maps each digit from 0 to 9 to another digit, indicating how each digit in number can be replaced. Our goal is to select exactly one non-empty substring of number and replace all the digits in that substring with their corresponding values from the change array. The key is that, after performing this replacement, the resulting string must be lexicographically the largest possible. The task is to return this largest string as the output. The input constraints ensure that the length of number can go up to 100,000 characters, and each value in change is between 0 and 9. Let's explore some examples to better understand how this mutation works and how to approach the problem. In the first example, we are given number as 132 and the change array is 9, 8, 5, 0, 3, 6, 4, 2, 6, 8. The change array specifies that the digit 1 can be replaced with 8, 3 with 0, and 2 with 6. To maximize the value of the number, we can choose the entire substring 132 and replace each digit using the change array. Specifically, 1 is replaced with 8, 3 is replaced with 0, and 2 is replaced with 6, resulting in the string 832. This is the lexicographically largest string we can get after the mutation. By analyzing this example, we see the importance of carefully choosing the substring to mutate and ensuring that every digit in the chosen range is replaced for maximum impact. Now, let's look at the second example, where number is 021 and the change array is 9, 4, 3, 5, 7, 2, 1, 9, 0, 6. Here, the change array specifies that 0 can be replaced with 9, 2 with 3, and 1 with 4. To achieve the largest possible number, we select the substring 021 and replace each digit. Specifically, 0 becomes 9, 2 becomes 3, and 1 becomes 4. This transformation results in the string 934, which is the lexicographically largest value we can obtain. This example highlights how the change array maps digits to their new values and how selecting the right substring to mutate is critical to maximizing the result. In the third example, the input number is 5, and the change array is 1, 4, 7, 9, 3, 6, 7, 2, 8, 9. The change array tells us that the digit 5 can be replaced with 6. Since the input string contains only one digit, we have no choice but to replace 5 with 6, resulting in the output string 6. This example is a simple case that emphasizes the importance of applying the change to the entire string when there is only one digit. It also demonstrates the edge case where the input string is minimal in size. Finally, let's discuss some important edge cases to keep in mind. If number consists of only one digit, as we saw earlier, you must decide whether to replace it or leave it as is, depending on whether the replacement increases the value. If the change array maps every digit to itself, meaning change x equals x for all x, no mutation is possible, and the output will simply be the same as number. When the optimal substring to mutate includes the entire string, all digits must be replaced accordingly. However, if the best substring to mutate starts or ends mid-string, it is important to stop the replacement process at the exact right location to avoid lowering the overall value of the number. These cases illustrate how crucial it is to carefully analyze the input and apply the mutation process efficiently to achieve the desired result. To begin, let's consider the brute force approach as an initial attempt. The intuition here is straightforward but computationally expensive. We generate all possible substrings of the input number, and for each substring, we apply the given mutations using the change array. The change array essentially maps each digit to its mutated value. Once the mutations are applied, we compare the resulting numbers to find the largest one. The steps for this approach involve iterating over every substring, mutating the digits within it, and keeping track of the maximum value encountered. However, this method is very inefficient. Given that a string of length n has O, n squared, substrings, and mutating and comparing each substring takes O, n, the total time complexity becomes O, n cubed. This makes it impractical for larger strings, as the computational cost grows exponentially. Overall, while simple, this approach is not feasible for real-world scenarios due to its high time complexity. Now, let's explore a more efficient solution using the greedy approach. The key observation here is that we don't need to evaluate all substrings explicitly. Instead, we can focus on transforming the digits of the number in a single pass to maximize the result. The strategy is to find the first position where mutating a digit improves the value, continue mutating as long as it remains beneficial, and stop as soon as further mutations no longer increase the number. This is based on the mapping defined by the change array, where each digit has a corresponding mutated value. If the mutated value of a digit is greater than the original digit, it's beneficial to mutate, otherwise, it's not. By leveraging this insight, we can efficiently construct the largest possible number without the need to consider every potential substring. The implementation steps involve traversing the string, mutating digits when it's advantageous, and appending the rest of the original string once the mutation ends. This approach ensures that we focus only on the relevant portion of the number, eliminating unnecessary computations. This optimized greedy approach has a time complexity of O(n), where n is the length of the input string. This is because we only traverse the string once, making it highly efficient even for large inputs. However, with any strategy, there are trade-offs. The primary advantage of the greedy approach is its efficiency and simplicity. It handles large input sizes seamlessly by avoiding exhaustive computations. On the downside, this method assumes that the largest number can be achieved by mutating a single continuous substring. While this assumption is valid for the current problem, it may not generalize well to other scenarios with different constraints. Ultimately, the greedy approach is chosen because it directly aligns with the problem's requirements. Instead of evaluating all substrings, it focuses solely on the mutations that contribute to the optimal result. This balance between simplicity and performance makes the greedy method the clear choice for solving this problem effectively. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. This implementation solves the problem of finding the largest number after mutating a substring of the input string number. We are provided with a mapping change that specifies how each digit from 0 to 9 can be transformed. 1. The function maximum number takes the string number and a list change as inputs. 2. The length of number is stored in n, and number is converted into a list to allow in-place mutation of digits. 3. A flag mutating is initialized to false to track whether we are currently mutating a substring. 4. We iterate over each digit in number using a for loop. The current character is converted to an integer and stored in digit for comparison. 5. If the mutated value change, digit, is greater than the original digit, we replace it in the list and set mutating to true, indicating we have started mutating a substring. 6. If the mutated value is smaller than the original and we are already mutating, i.e., mutating is true, we break out of the loop because mutation cannot restart once stopped. 7. After completing the loop, the list number is converted back to a string using join and returned as the result. This approach ensures that we maximize the number according to the problem's constraints while adhering to the rules of contiguous substring mutation. It has a time complexity of O(n), as we traverse the string once. This is the Java implementation for LeetCode problem number 1946, largest number after mutating substring. The logic mirrors the provided Python solution, but adheres to Java-specific conventions such as using character arrays for string mutation and explicit type declarations. The code efficiently traverses the input string, applies the mutation based on the change array, and stops when further mutation would not yield a larger number. To begin solving this problem, we start with the input number as 132 and the mutation rules provided in the change array. The first step is to convert the string number into a list of characters, which makes it easier to manipulate individual digits. Here, number becomes 1, 3, 2. We also initialize a flag, mutating, which is set to false. This flag helps us track whether we are currently in the process of mutating a substring. Now, for the first iteration at index 0, the current digit is 1. Using the mutation rules, we see that change, 1, is 8. Since 8 is greater than 1, we replace the digit at index 0 with 8. At this point, we set mutating to true, indicating that we have started mutating the substring. After this step, the state of number becomes 8, 3, 2. In the second iteration, we move to index 1, where the current digit is 3. Referring again to the mutation rules, we find that change 3 equals 0. Comparing 0 with the current digit 3, we see that the mutated value is smaller. Since the mutated digit is not greater and the mutating flag is already set to true, we decide to stop mutating at this point and exit the loop. After exiting, we convert the number list back into a string format, resulting in 832. This is our final output for this example. Now, let's look at a different example where number is 021 and the mutation rules are provided in the change array. As before, we first convert number into a list of characters, resulting in 0, 2, 1. The mutating flag is initialized to false. During the first iteration at index 0, the current digit is 0. According to the mutation rules, change 0 equals 9. Since 9 is greater than 0, we replace the digit at index 0 with 9 and set the mutating flag to true. The updated state of number is now 9, 2, 1. Next, in the second iteration, we examine the digit at index 1, which is 2. From the mutation rules, change 2 is 3. As 3 is greater than 2, we update the digit at index 1 to 3. The state of number becomes 9, 3, 1. Moving to the third iteration at index 2, the current digit is 1. Here, the mutation rules specify the change 1 is 4. Since 4 is greater than 1, we replace the digit at index 2 with 4. After all iterations, the state of number becomes 9, 3, 4. Finally, we convert this list back into a string, yielding the output 934. In this third example, the input number is 000, and the mutation rules are provided in the change array. After converting number into a list, we have 0, 0, 0. The mutating flag is initialized to false. During the first iteration at index 0, the current digit is 0. Referring to the mutation rules, change 0 equals 1. Since 1 is greater than 0, we update the digit at index 0 to 1 and set the mutating flag to true. The state of number is now 1, 0, 0. In the second iteration, the current digit at index 1 is 0. The mutation rules specify the change 0 is 1. Comparing 1 with 0, we see that 1 is greater, so we update the digit at index 1 to 1. The state of number becomes 1, 1, 0. In the third and final iteration, the current digit at index 2 is also 0. Again, the mutation rules indicate that change 0 is 1. Since 1 is greater than 0, we replace the digit at index 2 with 1. The final state of number is 1, 1, 1. Converting this back into a string gives us the output 111. The time complexity of this solution is O, n, where n is the length of the string number. Let's break this down step by step. First, converting the string number to a list takes O, n, because we iterate through the entire string to create a list of characters. Next, we have a single for loop that iterates through each digit in the list, which also executes at most n iterations, making this step O, n. Inside the loop, operations like converting a character to an integer, comparing two values, and updating the list are all constant-time operations, or O1. While the loop may terminate early if certain conditions are met, in the worst case, it still runs for all n iterations. Finally, after the loop, we convert the list back into a string using the join method, which again takes O, n. When we sum up all these steps, the dominant factor is O, n, making the total time complexity O, n. When we consider the overall time complexity, all the major steps in the solution involve O, n, work, so the total time complexity is O, n. This remains consistent for the best, average, and worst cases because the loop runs linearly in all scenarios. Now, let's analyze the space complexity. The space complexity of this solution is also O, n. Here's why: the input string number itself has a size proportional to n, but since this is part of the input, it doesn't count as additional space usage. However, when we convert the string to a list, we create a new data structure that also requires O, n, space. Beyond that, the solution uses a few simple variables, like integers and booleans, which take negligible O1 space. Finally, the output string, reconstructed from the list, also requires O(n) space. So, the dominant factor in space usage is the list created from the input, leading to a total space complexity of O(n). To understand the efficiency of the optimized solution, let's compare it to a brute force or naive approach. A naive solution might involve generating all possible substrings of number, mutating each one, and comparing the results to find the largest number. Generating all substrings for a string of length n involves approximately n squared substrings, which would take O(n) squared time. Then, for each substring, mutating and comparing would require O(n), making the total time complexity O(n) cubed. In contrast, the optimized solution avoids generating substrings entirely. Instead, it uses a single linear pass through the string. By mutating digits in place and only performing necessary comparisons, the optimized solution achieves O(n) time complexity. This represents a significant improvement over the O(n) cubed time complexity of the brute force approach, while maintaining the same O(n) space complexity. The time complexity remains O(n) across the best, average, and worst cases, but the behavior of the loop differs slightly in each scenario. In the best case, the loop terminates early after mutating only a small prefix of the string. However, since converting the string to a list and joining it back into a string still take O(n), the overall time complexity is O(n). In the average case, the loop may perform mutations for a middle portion of the string, but even here, the time complexity remains O(n) due to the linear nature of the operations. In the worst case, the loop iterates over the entire string, mutating every digit. Even then, the time complexity is still O(n). The space complexity also stays consistent at O(n) in all cases because the list representation of number and the final output string dominate memory usage. Mathematically, the O(n) time complexity arises because the loop contains only O(1) operations and iterates at most n times, while space complexity is O(n) due to the list and output string. When solving this problem, there are a few common mistakes to watch out for. First, overlooking edge cases is a frequent issue. For example, you might forget to handle empty strings, single character inputs, or cases where no mutation can produce a larger number. These scenarios can lead to runtime errors or incorrect outputs, so always test your solution with both minimal and extreme inputs. Another common mistake is incorrect mutations, such as misapplying the change array. This could happen if you accidentally use the wrong indices or apply transformations outside the valid range. Double-check your mapping logic to ensure that all indices align correctly to avoid these errors. Inefficient substring generation is another pitfall to avoid. If you generate all possible substrings without optimizing, it can result in O(n) cubed complexity, which is impractical for larger inputs. Finally, failing to reset the state of the original number during mutation trials can cause cascading errors. It's critical to ensure that the original input remains unchanged unless explicitly intended to be modified. Another mistake to be cautious of is improper comparison logic. If you compare numerical strings lexicographically instead of converting them into integers, you might end up with incorrect results, especially for numbers with leading zeros. Always handle numerical string comparisons carefully to avoid this. Now, let's talk about some useful interview insights. Pay close attention to the constraints provided in the problem. For example, if the constraint specifies that the input length can go up to 10,000, this indicates that brute force methods likely won't be optimal, and you should focus on more efficient approaches for substring generation or mutation operations. Additionally, be prepared to explain the trade-offs in your solution. For instance, you might prioritize readability over performance in certain edge cases or vice versa. This demonstrates that you have a deep understanding of the problem and the implications of your approach. Lastly, during an interview, explicitly test your solution with edge cases, like when no mutations are possible or when all digits are already maximized, to showcase the robustness of your implementation. This problem also shares similarities with a few other LeetCode problems, which can provide valuable practice and insights. For example, LeetCode 670, maximum swap, is another numerical transformation problem where the goal is to maximize the number by swapping digits. Similarly, LeetCode 1328, break a palindrome, involves mutating strings strategically to achieve a specific outcome. Another related problem is LeetCode 402, remove k digits, which focuses on minimizing a number by removing certain digits. Lastly, LeetCode 2273, find resultant array after mutations, involves applying transformations to an array, a concept that parallels the digit mutation process in this problem. To approach this problem from different angles, you could explore alternative strategies. For instance, an optimized sliding window technique allows you to analyze potential transformations in O(n) time, avoiding the inefficiency of generating all substrings. A greedy strategy could also be effective, where you prioritize the largest possible transformation for each digit sequentially. While this avoids exhaustive substring generation, it's important to ensure correctness in all variations. For more complex scenarios, dynamic programming can help by tracking the maximum possible number at each step. However, DP may be overkill for this problem if simpler strategies, like the greedy approach, are sufficient. When deciding on an approach, it's important to weigh the trade-offs between different strategies. Brute force methods, while simpler to implement, are computationally expensive for large inputs and may not meet performance constraints. Optimized techniques, such as sliding window or greedy strategies, are much more efficient but often harder to implement correctly. Another consideration is the balance between space and time complexity. For example, dynamic programming can reduce computation time by leveraging pre-computed results, but it typically requires additional memory. Always consider the specific constraints provided in the problem to choose an approach that strikes the right balance between simplicity, efficiency, and correctness. Great job! To wrap up, we discussed the solution to the problem and key points to remember, including substring manipulation techniques and optimization strategies. Keep practicing and expanding your problem-solving skills. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!